When traditional polyolefins run through a twin-screw extruder, the process is highly predictable. The machine pulls in the raw resin and standard additive packages, melting them into a uniform flow that yields smooth, continuous strands at high speed. But over the past decade, sustainability mandates have forced manufacturers to replace these stable plastics with biodegradable polyesters like PLA and PBAT. Operators often try to run these biopolymers using the exact same machine profiles they used for polyethylene. The result is immediate physical failure.
OnlyTRAININGS. Learn what works in the industry.
Melt pressure surges, the polymer discolors, and the extruded strands become brittle and fracture at the die head. This is the drop-in fallacy, the assumption that a biodegradable polymer can serve as a direct one-to-one replacement for a traditional plastic. Bioplastics have entirely different thermal limits. Applying generic additive packages and standard temperature profiles to these materials guarantees structural collapse, wasted R&D budgets, and unusable end products. The root of this failure usually starts in the lab. Compounders often treat the chemical formulation as one isolated task and the mechanical extrusion settings as another. You cannot separate the chemistry from the machine. Successful biopolymer compounding demands that the material and the extruder be treated as a single, tightly coupled system. We can see this relationship clearly in this network map. The chemical formulation nodes, the specific polymer combination and additive ratios, are directly linked to mechanical inputs like the screw configuration, shear history, and barrel moisture levels. Altering one node instantly affects the others. To successfully scale production, we have to map the specific thermal and rheological boundaries of the core biopolymers, PLA, PBAT, PHA, PBS, and thermoplastic starch. Preventing polymer degradation requires mapping these interactions precisely. Stable bioplastics are the product of applied systems engineering. Take polylactic acid, or PLA. On its own, it has notoriously poor melt strength and is highly brittle, making it difficult to process into flexible films or durable molded parts. Compounders add reactive chain extenders to build molecular architecture. This matrix maps the safe operating zone for extension, plotted against temperature and shear. If mechanical shear or temperatures increase excessively, the reaction reverses. Heat triggers hydrolytic degradation, instantly breaking polymer chains and destroying the compound. To compensate for that inherent brittleness, formulators typically blend PLA with PBAT, an elastomer that introduces necessary toughness. But PBAT brings its own processing demands. A PBAT-heavy blend requires precise temperature control to maintain structural stiffness and manage material costs. Because PLA and PBAT are distinct polymers, they do not naturally mix. Forcing them together under mechanical shear makes controlling the phase morphology, how the two materials physically interact on a microscopic level, incredibly difficult. A stable PLA and PBAT blend requires compounders to manipulate the extruder's mechanical shear history just as aggressively as they adjust the chemical additive ratios. While PLA and PBAT are sensitive, polyhydroxyalkanoates, or PHA, and PHBV are highly volatile. Under uncontrolled heat, these organic solids melt down and structurally degrade. Returning to the matrix, we see the operating constraints for PHA. The thermal boundary box is incredibly narrow, allowing almost zero margin for error. The exact moment barrel temperature exceeds this boundary, the polymer experiences catastrophic loss of molecular weight, becoming a useless liquid. Managing this requires strict mechanical control over residence time. The polymer cannot stay inside the heated barrel a second longer than necessary to melt and mix. With PHA formulations, the physical dimensions and capabilities of the extruder dictate whether a chemical formulation can survive the manufacturing process. Thermoplastic starch, or TPS, introduces a completely different variable: extreme moisture sensitivity. Water acts as a necessary plasticizer to break down the rigid starch granules, but excessive moisture left in the melt acts as a destructive agent. If that moisture is not meticulously managed before the material exits the die, the compound experiences massive viscosity drops and structural foaming. This longitudinal cross-section of a twin-screw extruder shows dedicated venting zones positioned to extract vapor during the melt phase. Operators must time devolatilization perfectly. Venting must extract excess water upward as vapor, without prematurely removing the moisture required to plasticize the starch structure. Failing to achieve this precise moisture balance causes the starch to agglomerate, preventing any added fillers from dispersing evenly through the compound. To ensure proper dispersion in these starch-rich compounds, operators use split-feeding strategies, introducing different additives at specific points along the barrel rather than all at once. Scaling TPS production requires precise management of fluid and vapor dynamics inside the machine, a completely different discipline than traditional dry blending. PBS and PBSA represent another balancing act. They are highly valued for their fast crystallization kinetics and flexibility. However, the standard nucleating agents that industry relies on for polyolefins fail completely when introduced into the complex matrices of these biopolymers. Formulators use engineered compatibilizers. This diagram shows a targeted chemical compatibilizer acting as a bridge, locking an incompatible PLA phase with a PBS phase. But screw configuration dictates whether that bridge survives. Aggressive kneading blocks generate high shear that physically fractures the compatibilizer. The chemistry becomes even more fragile when adding natural fiber reinforcements, which often trigger antagonistic reactions with the compound's stabilizing additives. A highly advanced chemical additive package is useless if the mechanical shear profile tears its functional chemistry apart before the plastic reaches the pelletizer. Every decision made at the compounding stage ripples through the entire production pipeline, from the base resin selection down to the final commercial product. This continuous loop shows how polymer blending, additive engineering, twin screw parameters, and downstream conversion are intrinsically linked. They operate as a single ecosystem. When blown film bubbles collapse or injection molded parts warp, the root cause is rarely the converting machine. It is almost always a subtle misalignment during the initial compounding phase. Relying on generic rules and trial and error to fix these issues leads to wasted material and lost production time. Professional formulation relies on systematic, data-driven decisions. Scaling bioplastics reliably means abandoning the practice of isolating variables. It requires holistic, predictive process control over both the chemistry and the machinery. Navigating these strict thermal limits, fluid dynamics, and shear sensitivities requires advanced industry-specific data that goes far beyond general polymer science. The Biopolymer Compounding, PLA, PBAT, PBS, PHA, and TPS training from OnlyTRAININGS provides the exact technical blueprint for this process. This curriculum is not theoretical. It is designed and taught by active compounding professionals and industry process engineers who scale these materials daily. The sessions deliver actionable insights on practical twin screw process design, mastering filler dispersion, and diagnostic troubleshooting for real melt processing operations. Enrollment includes 6 months of full platform access, downloadable technical toolkits, and a 24/7 direct connection to the experts to clarify your specific formulation challenges. Click the link in the description to stop guessing at parameters and start engineering stable, high-performance biocompounds today.